Continuing on in section 8.1, in example 4, we're going to be adding polynomials. A researcher studied the number of overnight stays in U.S. National Park Service campgrounds and in the backcountry of the National Park System over a 5-year period. The researcher modeled the results in thousands with the following polynomials. So campground and backcountry are there. In each polynomial, x equals 0 corresponds to the first year of the 5-year period. That just tells us that this is all based off of when he started, so it's not using years as in like 2014, it's using years in terms of 0, 1, 2, 3, 4, 5. What polynomial models the total number of overnight stays in both campgrounds and backcountry? So total here means that we are going to add these up. And when we add polynomials, there's a couple different ways that we can do it here. So the first way I'm going to show you is by using columns. So here I look at my degrees. I have degree 2, 1, 0, degree 2, 1, 0. So I make a column for each degree I have. I have degree 2, I have degree 1, I have degree 0. Now each polynomial gets its own row. So here's my first one. Here's my second one. They each get their own row. Now we just fill in our values to those columns. So I have negative 7.1 x squared, it goes in my degree 2. Negative 180x, degree 1. And remember, the signs go with your numbers. And 5800 is degree 0. For my second polynomial, I have 21x squared. So again, it goes in my squared column. Negative 140x and 1900. Now, because we're finding the total and adding, total means we add, we are going to add up all of our columns here. My x squareds, same variable, so I keep my variable, add my number parts, keep my variable, add my number parts. Here, same signs, both negative, so it's negative 320. Here, same signs, so I add them up. 7,700. And this polynomial right here is our total number of overnight stays in both campgrounds and backcountry. The other way we could have done this, guys, is just by combining our like terms. So looking at our two expressions in their entirety and finding the things that are alike and putting them together. So I like to do this by going through and kind of labeling them a little bit based off their degree. So I would say I have x squareds, those go together. I have x's, those go together. And I have constants, those go together. Now I just combine them just like they're written. You could also rewrite this so that they're all on one line. And then we're going to add. And again, we can then, based off our degree, combine our like terms. So I'm going to go ahead and mark, just like I did when they were here, things that go together. Now, I can take my x squared and my x squared, and I get 13.9 x squared. I can take my linear factors, degree 1, together. And I can take my constants and add those together. And I get to the same place, guys. It's just sometimes these columns help us keep a little bit more organized, especially when we start to get into higher degree polynomials and polynomials that may not be in standard form or that are missing some terms, like maybe they don't have a linear term. So sometimes it's a little bit helpful to use the columns just to help us keep track of things a little bit easier. Now, feel free to pause here and give this a try if you'd like. A nutritionist studied the U.S. consumption of carrots and celery and of broccoli over a 6-year period. The nutritionist modeled the results in millions of pounds with the following polynomials: carrots and celery and broccoli. In each polynomial, x equals 0 corresponds to the first year of the 6-year period, meaning when we started, not like the calendar year. What polynomial models the total number of pounds in millions of carrots, celery, and broccoli consumed in the United States during the 6-year period? So again, we're finding total. So I'm going to take my carrots and celery and add it with my broccoli. So to use columns here, I'm going to check my degrees. 3, 2, 1, 0, 2, 1, 0. So 3 is my highest degree. That's what I start with. And then I make a column for everything after it. Even if there isn't any linear factors, no degree 1s, we still want to have the columns from 3 all the way down to 0, or whatever our highest degree is down, because there might be in an expression later, even if there isn't in the first one. So I'm going to fill in my spots here. Carrots and celery, we'll do green. Negative 12x cubed. 106x squared. Here my degree is 1, so I put it in my degree 1 column. And 4477 is my constant. And again, all of the things in one polynomial get one row. Broccoli, I have 14x squared, so I put that in my squared column in my degree 2. I have minus 14x, and I have 1,545. Now, because we're finding the total, I'm going to add up each of my columns. And if we don't have something there, guys, we can go ahead and plug in a 0. You don't have to if you don't want to, but for some of you, it's going to be helpful to be able to see that. So if you want to, go ahead and put in that 0. Now we can add up our columns. Negative 12 plus 0 is negative 12, and we keep our variable exactly the same. Here, these are both x squared, so I keep my x squared, combine my number parts. Both x's, so I keep my x, add up my number parts. And neither one of these have a variable, so they're like constant terms. I can go ahead and add those up. 6,022. And this is the total carrot, celery, and broccoli. We also could have just listed these all out. I could have done negative 12x cubed plus 106x squared minus 241x plus 4477. Total means we're going to add 14x squared minus 14x plus 1545. We get to have a lot of different terms here, and we have to figure out which ones go together. So I only have one x cubed term, x squareds and x squareds, x's, and constants. So again, when we start to get more terms, it's a little bit harder to keep track of things, especially when all you have is a pencil, one color. Here I can keep them differentiated by color and by little shapes or things underneath them. But if it's easier for you to put them in the columns just to help you keep organized, then feel free to do that. So here, again, I would have negative 12x cubed. With my x squareds, I would combine my number parts, keep my variable. With my linear factors, my just x to the first power, 255x. And for my constants, those without variables, I would add those up and get 6,022 as well. So I get to the same answer regardless of whether I added in columns or in a line and combine my like terms. That part doesn't matter as long as you can get there, whatever helps you keep organized and to make sure we don't miss any pieces. In example 5, we're going to be subtracting polynomials. So we're looking for a simpler form here of a polynomial minus a polynomial. And we can tell these are polynomials because the parentheses tell us that x cubed minus 3x squared plus 5x go together. And 7x cubed plus 5x squared minus 12 go together. So just like we did before, I'm going to check my degrees. Here I have 3, 2, 1, 3, 2, 0. So 3 is my highest degree. That's going to be my first column. And again, even though in my first polynomial, for example, I don't have a constant term, degree 0, I still want to put that column because sometimes it will be there in our second one. So here in my degree 3, I have x cubed minus 3x squared and 5x. I have 7x cubed, 5x squared, and negative 12. And make sure we keep them both in the same row. All of the things that are one polynomial go on one row. And we want to make sure that we get them into the right column. So we don't just go necessarily right in order. Like our 12 here, negative 12, we had to make sure went in our constant, our degree 0 column. Now, because we're subtracting, I'm going to subtract each column. And when I subtract a negative, we actually add. So minus a negative is going to give me a plus. And here we can put a 0 if you want. You don't need to. Same thing here. I can put a 0 if we want. You don't have to have those, but if that's easier for you to see what we're doing here, then go for it. So here I'm going to have 1 minus 7, which is negative 6, and then I keep my variable. Negative 3 minus 5 gives me negative 8. Keep my variable part. 5x minus 0 is still 5x. And 0 minus a negative 12 or plus 12 gives me a positive 12. Okay. If we're going to do this one all in one line, we still can. We can take x cubed minus 3x squared plus 5x. And then we take 7x cubed plus 5x squared minus 12. But don't forget that we are still subtracting the entire second polynomial. So we subtract the 7x squared. We subtract the 5x squared. And we subtract, minus a negative again is a plus, the 12. We have to take that negative, just like if it was a negative 1 and we distribute it in. Same idea here. We have to take that to everything that follows. And then we can combine our terms. So x cubes go together. X squareds go together. I only have one x linear term and one constant term. So x cubed minus 7x cubed is negative 6x cubed. Negative 3 minus 5x squared is going to give me negative 8x squared. I just have a 5x, and I just have a 12. So we got to the same place no matter which way you used, but do not forget, I'm telling you, some of you are going to forget, don't be the person who does it, that we have to take that negative to everything in the polynomial that follows. We're subtracting that entire polynomial. Now feel free to pause here and give this a try if you'd like. My first polynomial has degree 3, second one degree 2. So I'm going to start off with 3, 2, 1, and 0. I'm going to put my degrees in descending order, starting at the biggest one I have showing, which is 3. Then I'm going to fill my values. So I have negative 4m cubed. A negative m goes in my linear factor. Remember, my degree there is a 1, and then a 9. Second one, I have 4m squared, so it goes in my squared column, but remember, it's its own polynomial, so it gets its own row. I have an m, and I have a negative 12. Now, we are subtracting, so I'm going to subtract in all of my rows. Minus a negative gives me a plus. And remember, if it's easier to put in those zeros, you sure can, but you don't have to. And now I can combine them. Negative 4 minus 0 is negative 4m cubed. 0 minus 4 is negative 4m squared. Remember, there's 1s as our coefficients if they're not shown. So I actually have minus 1, which gives me negative 2m. And 9 minus a negative, or plus 12, gives me a positive 21. And this is my solution. Again, remember, if you're going to list them all out, we put our first polynomial, and then our second polynomial, but since we're subtracting the second polynomial, we have to subtract every piece there. Okay, we have to subtract the entire polynomial. From here, we can combine our like terms. M cubed, I just have the 1. M squared, I just have 1. M's, I have 2. And constants, I have 2. So when I combine them, I get negative 4m cubed minus 4m squared minus 2m and plus 21, the same way I did with columns. So it really just depends on if you can remember that we have to subtract all those when they're listed or in their columns. And however it is, that helps keep it organized for you. Real quick recap here on section 8.1. Monomials can be used to form larger expressions called polynomials, and polynomials can be added and subtracted.